In this lecture, I want to discuss the problem of changing the set of coordinates from Cartesian to another set. I will start with addressing the fact that in general, when we have to compute an integral, a double integral, in general we have a function like f of xy times dx dy, and we want to transform this integration by changing coordinates. The new coordinate v will be a function of x and y, and then we can use w, for instance, when w is a function of x and y as well. And then we want to transform the integral in terms of the new variables, v and w. So we will have something here, and then there will be the area dw dv. In case of a single variable, we had an integral of the kind f of x dx. When we make a substitution, this is pretty easy. If we set a new variable t as a function of x, then what we need to do is just take the derivative of t with respect to x, so dt over dx will be t prime of x. So this is a function of x, and dt, our differential, divided by t prime of x is equal to dx. And t prime of x is our derivative in terms of x. We have t equals t of x, but we could also express x as a function of t. And in this case, we have dx over dt, I mean the derivative of x with respect to t is equal to x prime of t. In this case, it's a derivative in terms of t. So this is what we want, because I can write it as dx equals x prime of t dt. And in this case, this is a function of t. In this case, this was a function of x. So in here, I have integral of f of x of t. So I have to express x as a function of t, and then I have x prime of t dt. If I have some boundary values, then I need to change the values, passing from x to t, or vice versa. For instance, if I set a and b here, when x is equal to a, t is equal to t of a. So in here I should put t of a. Whereas in here, you can just simply imagine that I should put t of b. That's pretty easy when I consider single variable calculus, but with multiple integrals, this becomes a little bit trickier. It's an extension of this idea, but it's more complicated than that. We will try to understand what's going on by analyzing this object here, the area dx dy. If we do that, the idea is much simpler to analyze. In general, what this means is that we are considering small areas. This is a rectangle with base dx and height dy. This is the plane xy. Then we are multiplying this small area by a height that goes along the z-axis, where my function is defined, f of xy, so that I can obtain a parallelepiped. And then I sum the volumes of all those parallelepipeds to obtain the entire volume given by the integration, the double integration. But when I switch to another set of coordinates, this area changes in general. If I think about what happens to these kind of areas, in this case I will have another plane, and my plane will be the plane uw. In general, since w and u are functions of x and y, if the transformation is not linear, these sides do not remain lines in the uw plane, but they can become curved, so I can obtain something like this. This will always be something very small, so it's infinitesimal. And when I consider infinitesimal quantities, these will almost remain lines. So they can be curved in general when I consider finite dimensions, but when I consider very small quantities, I can still interpret these as lines. For instance, this is one side of the rectangle, and then this other side can become this other one. My rectangle can become something like this. It can change its shape. This is very important. We need to understand how to treat this area. So what's this area? This area is not dw du, because dw du would be just something like this. This is the uw plane, so this is du and this is dw, and this is due to the transformation, which does not allow me to say that dx dy becomes equal to dw du. And we will use cross products to make this sort of transformation. The area of a parallelogram can be computed by taking the cross product between the two vectors that constitute two sides of the rectangle, in this case, or the parallelogram. Let me call this the vector v1, this v2. So the area of this rectangle is the magnitude of the cross product between v1 and v2, or v2 cross v1, doesn't matter in this case because we take the magnitude. v1 in the case of this rectangle here would be equal to a vector with component dx and 0, whereas v2 would be a vector with components 0 dy. In this case, the cross product is just the determinant of this vector here. It's dx 0 0 dy, and this is equal to dx dy. But what happens when we go to the WU plane? We should consider the transformation. So we have dx. X can be thought as a function of v and w. In here I call this x-axis u, but I said that x and y can be thought as functions of v and w. Right here it doesn't really matter, it depends on the way I want to name my axis. So if you want I can call this v or u. Let's call this v to remain consistent, but doesn't really matter. So I will call the x-axis in the new set of coordinates v instead of u. So I will use v and w. X can be thought as a function of v and w, so this is the differential of a function, and this can be written as dx over dw plus dx over dv. And so for dy is equal to dy over dw times dw plus dy over dv. And this is something that I will analyze right here. In particular, let's redraw the parallelogram in the VW plane. Here we are, VW. I can compute a cross product to obtain the area of this parallelogram. So I will call this vector V1, I will call this vector V2. So the area of the parallelogram that I want to find is V1 cross V2. But in this case it will not be equal to dx dy, it will be a function of v and w. What is V1? V1 has some components along v and has some components along w. The component along v, this component right here, is related to the change of x and y along v. In particular, this side becomes equal to this one, so this is dx over dv, whereas this other part is due to the change of x along w. So this is dx over dw, so this is just due to the change of x, this vector right here, not of y. Whereas this other vector, v2, is due to the change of y, because this side here becomes this one. In this case, the component along w is just dy over dw, whereas this component right here is just dy over dv. If I want to compute this cross product, v1 is just simply equal to dx dv, and we should also multiply this by dv, whereas this one should be multiplied by dw, because this is the change in x. The change in x can be seen from this expression. Dx changes because some part of it changes along w, some part of it changes along v, as you can see from here. This is a change along v, this is a change along w. And the same can be done here, so we should multiply this by dw, and we should multiply this by dv. So the component along v of v1 is dx over dv times dv. The second component along w is dx over dw times dw. Whereas for v2 we have the component along v is dy over dv, and then here we have dy over dw. We should take the cross product of this. So the cross product, the area of that parallelogram, this is a transformation of coordinates, so this area will also remain equal to this one, because this is just a change of coordinates. Our dx dy will transform to this other area right here, so they are the same, they should be the same when I make this sort of transformation in the integral. So we have dx dy that becomes equal to this area right here, which is equal to the cross product between v1 and v2, and that is equal to the determinant of this matrix, dx dv times dv, and dx dw times well, the second row is dy over dv, and then we have dy over dw. I get dx over dv times dy over dw, and then I have dv times dw minus dx over dw times dy over dv times dv dw. Okay, so I can factor out these factors. dv dw can be factored out of the determinant. I could also rewrite it as dx dv, dx dw, dy dv dy dw times dv dw. So this is the way that the area dx dy transforms by changing coordinates. And this has a very compact notation. This is called the Jacobian of the transformation. As you can see, we just take the derivatives of the first variable along the first row in terms of the new set of coordinates v and w, and then we take the second variable in the second row and compute the derivatives of this variable in terms of the new set of variables v and w, and this is called the Jacobian. Sometimes it's denoted like this, so it's dxy over dvw. It's the Jacobian of the transformation. The integral, the double integral, but this expression is just the same even in case of three variables, for instance, triple integrals. You should always compute the Jacobian, even in that case. The double integral f of xy dx dy computed over the region A, let's call it A, which depends on the domain x and y. This becomes equal to, when we make a transformation, to f of x, but x has been expressed as a function of v and w, and then y as a function of v and w, times the Jacobian of the transformation dxy dvw times dv dw, because the area becomes equal to this part and the function remains equal to itself, but we need to express the function in terms of the new variables. And the domain of integration changes to another domain because it becomes a of x of vw, y of vw, and we will try to see by showing some examples how to change this domain.